Everyone, my name is Haiyan Yu. Today my topic is about COSTAR, constrained optimization for stratified treatment rules in reducing hospital readmission rates. This work is cooperated with Professor Ping Yu from University of Oregon. Thanks to Jiao Xiang, Hongxia Miao, and Jinqi Yang. My contents outlined as follows. The first part is introduction, then mode and results. The third part is application, and finally, I give some take-home message. Now let's go to the first part. Here I introduce a toy example. This table shows a design. With the factor designs, we can connect data from randomized trials. There are two factors, metformin and glyburide. With those two factors, we can have 4 treatment combinations. In this table, 0 stands for the factor absent and 1 stands for the factor present. Take the fourth row, for example, with those two factors present, the treatment combination is A4. This table shows the examples of patients and their treatment regimen. There are 8 patients. This table shows the patient ID, age, and the treatment regimen. The treatment assignment is independent on their outcomes in clinical trials, as outcomes varied in observation data. Those datasets are collected from 30-day readmission of diabetes patients in 130-day U.S. hospitals for the year 1999-2008. The age ranges from 10 to 90. With those ages, we can divide the patients into 5 subclasses. In this table, the second column, A stands for the subclass. The U stands for the mean response of a subclass with a specified treatment. For the outcomes Y, 0 indicates the subject readmitted within 30 days and 1 if over 30 days. NA stands for the missing potential outcomes. For the query patient, the dash 9 represents the outcomes unknown, and the column YOBS stands for the observable outcomes. From this table, we can see that the individual outcomes are binary, and for the subclass with the specified treatment, the mean response is a continuous variable. For example, for the first patient, the mean response is 0.783. Our motivation. The stratified treatment rule is a design function from the data space to the optimal treatment. Suppose that the experimenter seeks to maximize the response for the solution, where f is an objective function with theta. For example, the mean response or the adjusted mean. Theta Lj is the coordinate in AJ of the stratified treatment rule, which is the treatment setting of subclass SL under the map theta. For a subclass SL, the response U is the mean of individual potential outcomes, conditional on the covariates X that in that subclass with the J treatment. To make the response of multiple treatment comparable, the covariates of the individuals are controlled in the estimation of average treatment effect on the treated, where J is the reference treatment and Yj is the potential outcomes of the individuals given the covariates X. There are 3 challenging issues. Although the observational data provides the outcomes of the administered treatment for each individual, we are yet to estimate the parameters of the potential outcomes for those individuals with other treatments. The difficulty for setting the objective function lies merely in the rapidness of the treatment regimen, when the generalization of the potential outcomes are unknown. The third challenging issue is that balancing the treatment regimen opportunity and the rapidness of the treatment regimen. more notations for the solution of the stratified treatment result. Since each subclass has an identical optimal treatment, the solution is also denoted as theta star for simplification. The relationship between U and Y is represented as this table. We can see that for each cell, the sample size is denoted as NLJ. For individuals, their individual outcomes are denoted as YLJ, and for the cell response of each subclass is denoted as ULJ. For all the subclasses, this table shows 3 subclasses and 4 treatment. We can estimate their mean response, and we can further obtain the solution with the objective function. The optimal of the treatment regimen for each subclass can be represented as the maximization. With mu LG star is effective, we can obtain the solution with the argument maximizing mu LG. There is a correlate balance on the treatment through minimizing divergence of the sample weights with a convex combination of the 2 functions, maximizing the treatment regimens and minimize the divergence. That is, maximizing the J function, where omega and eta are 2 parameters representing a trade-off between optimality and robustness, and controlling the level of AL norm regionalization of weights. Eta and omega belongs to Z. Z is a preset domain, and theta Li is the absolute value of phi Li. The weights stand for the relative importance of the patients for each subclass. Now let's go to the second part, model and the results. For each subclass, ULJ and HLJ are estimated with the data in the cell SLAJ. The constraint optimization for stratified treatment rules is formulated as this table, as this model, where omega is a Lagrange multiplier. That is a positive value, indicating the relative importance of the correlate balance. MK contains the case order moment of a given variable X of individuals with respect to the treatment level A G star from the target subclass L. CIK is the case moment function. Eta is a parameter controlling the level of L1 norm regionalization of weights. With that objective function, when the HL takes the KL divergence, the objective function can transfer into this one. To solve this model using the Lagrange multiplier, the model can be solved with the following equation. In this model, the constraints are integrated into the objective function with the Lagrange multiplier. Rest of the weights. Assume that the function is strictly convex. For phi positive, then every local solution is a global solution, and any global solution is unique if the constraints are constant. The first order condition of the equation yields the solution. For the sample weight of individual in the subclass, it obtains this solution, where lambda equals to lambda 0 minus 1, and lambda is a vector of Lagrange multipliers for the balance constraints. QLI positive is the base weight for individual I. Now let's go to an application. The case of those from a study on reducing 30-day readmission of diabetes patients. This figure shows the scatter plot of individual outcomes in multiple subclasses. Each subclass shows 102 individuals, and the dashed line shows the mean values of the outcomes in each subclass. The outcome with 0 indicates the individual readmission within 30 days, and 1 if over 30 days. The higher the mean value of the outcomes, the lower the ratio of the readmitted within 30 days. This figure shows the results of treatment response and the standard deviation of the estimation in each subclass. The subfinger A shows the results without weighting. B shows the results weighting on X, and C shows the results weighting on X and Y. Without weighting, the method COSTAR takes the parameters as 0. With weighting on covariance X, the algorithm obtains the weights with the outcomes unknown, and Y takes equal values, for example, 0.5, and the parameters take the optimal configuration. For example, eta takes 0.003 and omega takes 11.67. With weighting on both covariance and outcomes, COSTAR takes the centimeter. Those figures show the results of stratified treatment rules with the response versus subclasses. Nested uniform designs are used for configuring eta and omega. The response of subfinger B shows the optimal treatment, that is A3 in the green line with the subclass. Its treatment response is larger than those of the others in the same subclass. Without weighting, the results shows that it cannot be interpreted when comparable with the other two results. The patients in this subclass, it should take A3 than A4. Those figures shows the Pareto frontier of the negative variance of the estimation versus response. The smaller the area above the curve, the better the solution. The same type of symbols shows the response of individuals from a subclass. A blue box takes the setting of subclass 1 with A4. The solution in subfinger C has larger response and smaller variance than those in subfinger B. More techniques for configuring the parameters. Nested uniform designs are used for configuring the parameters eta and omega, and we can estimate the mean response with efficiency and consistency. Now let's conclude our presentation. There are 3 take-home messages. First, interpretability. Using the framework of potential outcomes, the stratified treatment rules seek to target a strategy and make the optimal decisions from multiple treatments for subclasses of similar patients. Secondly, generalizable to adaptive treatment. The outcomes in the observational data are viewed as an adaptive feature for weighting. Thirdly, efficient searching. The performance for searching optimal parameters guarantees the description of the stratified treatment rules and the efficiency of the solution. That's my talk. Thanks.